Welcome to ETD 61. Our main goal today is to be able to read solubility graphs and understand how those charts tell us about what's going on in the solution. So I've got points A and B on my solubility chart here, and you can see that it's got two solutions. Well, there's lots of solutions, 4 different solutes that are available, but all we care about today is we care about potassium bromide and potassium nitrate. You're going to tell us what would go on at points A and B for each of those, and then explain how their solubilities compare, especially if you look at their lines. So go ahead and sketch the graph, just the parts that matter, and then we'll try this one together after you've tried it yourself. As we dive into it, the biggest thing we should notice, of course, is you've got this solubility chart. And with the solubility chart, it's measuring 2 things. It's looking at the solubility, of course, how well it mixes with water, of course, the certain number of grams of solute in 100 grams of water, which is the same as 100 milliliters of water. Then we can see the other thing it compares, which is the biggest deal, is temperature, right? So if we look at the lines, typically we see lines that look like this. Reading the chart is pretty easy if you think quickly. If you have a point that's on the line, that means that it's at its saturation point. That's when the parking lot's full and you can't fit any more of that solute in the solution. If it is, of course, below that line, below the line means you could keep pouring more in. It is unsaturated. There are still parking spots that are available, right? Now, the other part of this, of course, that tricks people is if it's above the line. If it's above the line, that means that it's just saturated. That means that you're pouring in the salt or the solute, and it's just piling up at the bottom. Notice that supersaturated does not show up on this graph because supersaturated is a weird thing. Not everything supersaturates. So if it's on the line, it's saturated. If it's below the line, it's unsaturated. If it's above it, it's still just saturated. And it's telling you how much is getting poured into there. The other thing you should notice is the line is always increasing on this one. And if the line is increasing, that tells you an important thing. If I'm increasing the temperature, that means its solubility, how much I can fit in a solution, is increasing. Hey, that's a direct relationship. And this makes sense, especially with solutes like this, because if I have bigger parking spots, then bigger parking spots means I got more space to park in. And that's why, of course, warmer solutions, such as this graph, will be able to fit more solute in it. That's why we tend to heat things when we cook them, and they go into the solution and make the flavor of the soup. Right? But it can tell you more detailed quantitative information that you can get from it too. So if we look at these points, we can see there's point A. Okay? And all I care about today is potassium nitrate and potassium bromide. So the first thing is to recognize that this is a graph, and you can use the graph to make measurements. One thing you can see is it tells you how much solute is there. And we can see that that is exactly 50 grams of solute. But that's 50 grams of solute at a certain temperature in 100 grams of water, because this is a solution. It's always 100 grams of water, right? Now, that 50 grams is 100, but if I follow down, that's at, well, that measurement there, that's at 25 degrees, which is room temperature, 25 degrees Celsius. I guess I only need one at, right? That's for either of those solutions. Now, if we look at the potassium nitrate, we can see that point A compared to potassium nitrate's line is, well, it's above it, right? And if it's above it, that means it's saturated, which means that if we looked at that solution, we could get some good information out of it. In this, if I follow up that line, you can see it's just below 40. That means that there are 39 grams of potassium nitrate that are dissolved in solution, dissociated, right? And that also tells us if we add up to what it is, up to the 50, that means that there's 11 grams of undissolved potassium nitrate sitting on the side of the parking lot inside the beaker because it was a saturated solution. Potassium bromide is a slightly different story. If we look at potassium bromide, it's this line right here. And you can see that at point A, it's actually below it. And if it's below it, that means it's unsaturated because you haven't filled it up all the way yet. And that means that the whole 50 grams that you poured in there is completely dissolved. If I look at point B, you can see it's a different spot on the graph. That, of course, gives me a measurement. If I follow over, that's exactly 100 grams of solute, whatever it is, in the 100 grams of water. But that's at a certain temperature. And if I follow down from B, I can see that's at 90 degrees. So this is a warmer solution. As you look at those numbers, you can tell what's going on with potassium nitrate. Now, if I look at point B compared to potassium nitrate's line, I can see that, whoa, it's way below it. So that means that for potassium nitrate, 100 grams, it would be unsaturated. there are still parking spaces. Means 100 grams is dissolved, and I could still park more in there, right? If I look at the potassium bromide, we can see that, well, point B is actually right on its line at that temperature. So that means that it's at its saturation point. It's just at the point in the morning where the parking lot at the high school would be filled up, right? So this means this would have 100 grams of dissolved potassium bromide in it, and there'd be just one additional crystal at the bottom because it had just reached its parking spot was full. In the lab, you would find that little first crystal shows up at the right temperature. That's when the parking lot fills up because you just can't fit any more. And you should notice that both of these substances, they clearly have different solubilities because they have two very different lines. And anytime you see a line, you should be thinking of math class and your math teacher and these wonderful things called slopes, right? So if we look at the two lines and draw them quickly, we can see that we've got this thing called solubility, how well it parks, right? And we got this thing called the temperature, and we can increase the temperature, we can increase the solubility in those two directions. If I look at something like the potassium nitrate, the weird thing about its curve, you can see that it has a steeper slope. It goes up. It's not a hill I'd want to climb, right? Potassium bromide is a different story. Potassium bromide has a flatter slope. That's my kind of hill. Easier to climb. But this gives us very different information about both of these. If you look at KBr, potassium bromide, it actually has a higher solubility. More solute can fit at a lower temperature. When it's cold, it can actually park more into solution. If you look at the potassium nitrate, though, the potassium nitrate is more soluble when it's at a higher temperature, right? Whereas potassium bromide would be less. So the thing that we should notice is, as temperature increases, the solubility of potassium nitrate changes more. This means it has a steeper slope because temperature has a greater impact on potassium nitrate's solubility. And if I look at potassium bromide, it does well at low temperatures, but it does just about the same, only a little bit better at higher temperatures. So that means that temperature has, of course, less of an impact on potassium bromide solubility. And then my favorite question on the test would be, why, right? And you probably have to draw and explain. And if you ever wanted to explain what was going on here and why there was two different reactions to temperature, you just got to think about size, shape, and charge, right? If we look at potassium bromide, it's a diatomic ionic salt, right? It's made of two separate ions, which means it's really, really small. It's like a scooter, a Vespa, right? It's easy to park. If I look at potassium nitrate's got this thing called a polyatomic ion, a nitrate ion. It's got a 1- charge, but it's also got this thing called the potassium. So compared to my little tiny scooter, potassium nitrate is more like an RV. Which one would it be harder to park in? Well, that would depend on the size of the parking spaces, right? Potassium nitrate would do much better to park more of them if there was bigger parking spots, like at higher temperatures. Whereas you can park scooters at little spots or big spots, no matter what. It's easy to fit them in there, but you fill up pretty quickly because you're just going to be able to park them, right? So always consider when we're looking at solubility, size, shape, and charge. Look at the big old caboose on that thing, man. It's pretty hard to fit it in, whereas that little scooter's nice and small and can fit in. They're both very, very soluble because, of course, they have really nice charges for water, +1, -1. So this really comes down to size and shape, right? Things we need notes on. There's this thing called mass percent. It's pretty straightforward. You take the percent by mass of a solution that is solute. So a really good example would be, the calculation would be, you take the mass of the solute, and you divide it by the mass of the solute plus the mass of the solvent. That's what usually people forget. They have to add the solute with the solvent because that makes the solution. So it's the solute over the entire solution times 100. And that gives you the percent by mass that it is. A good example would be like 2% milk. 2% milk is 2% fat compared to the entire mass of the solution, which is why I don't drink 2% milk anymore, because that's a lot of fat. Now, other things that we have to target, of course, we look at the solubility curves on your homework. You can ask questions about that during our class meeting this week. One thing that we do need to know, of course, is this thing called molarity. We've been talking about this conceptual idea of solutions. Now it's time to get into the quantitative stuff, not just the qualitative stuff. And what molarity, which we have been writing on the beakers all year as a big M, That, of course, is the chemical representation of its concentration. So things that we can notice about molarity is molarity, of course, is a big M, and what it stands for is the moles of solute over the liters of solution. So it's technically the moles per liter. Now, my biggest hint for you is anytime this year that you see a big M in a question, you should convert it to moles per liter. It talks about a molar solution, a 1 molar solution. That's how many moles in a liter. If you turned it in moles over liters, doing the calculations is a lot easier. It'll hurt your brain less. So let's do a simple one together. Write down the question. You can pause me. Calculate the molarity of a solution prepared dissolving this many grams of sodium hydroxide in that much water, right? So anytime you're like, how do I solve this? Hey, dimensional analysis. It's your buddy, right? Figure out what you got and what you need. It wants us to calculate the molarity of this solution of sodium hydroxide. It tells me that I got this many grams. It tells me that I have this many milliliters of it, right? So if I need molarity, I'm going to need these things called moles over liters of sodium hydroxide at the end. That's where I'm trying to get to. That's what I need, right? What I got is I got this grams, I got the milliliters. I'm going to start with the grams because that's where the piles are, right? I got my 11.5 grams of the sodium hydroxide, and I want to convert it to that. Now, first thing I can do is get rid of this G thing and turn it into a mole thing. I'm going to take, of course, its molar mass and turn it into those piles. And the nice thing is 1 pile of that is exactly 40. It's one of the sweetest numbers on the table, right? Then the next step is that gives me the grams are gone. I'm stuck with moles on top, which is what I wanted, right? But now I have to put it in solution, which means that I can say, okay, how much is there? Well, 1,500 milliliters is the same thing as 1, 2, 3. That's 1.500 liters. Always turn it to liters, right? Now, what do I put on top? I don't have to put anything on top. If it makes you feel better, you can put a 1 on top and say for every 1 sample of solution, it's 1.500 liters, right? But I'm just trying to get liters on the bottom because I'm throwing it in solution. When you math that up, of course, you would get Siggy with it. You have 3 Siggies, and that would give you 0.192 moles per liter of sodium hydroxide, or I could write it the same thing as 0.192 molar sodium hydroxide, which is what we tend to write on solutions. It's both the same answer, right? So this is about going from grams to moles and then taking those moles and sticking them on top of liters. And that's the only new trick that we have to throw into this. So if you ever see an M, a big M, turn that big M into moles over liters and your life will be easy. Now the lab that we would have done, of course, as we looked into those, would have been this thing called the Alka-Seltzer Lab. And plop, plop, fizz, fizz, if you throw Alka-Seltzer into water, it'll quickly produce bubbles. That's because as it does that, it's reacting and producing carbon dioxide. The CO2 then goes into the solution, changing the flavor of it, and it goes as a solution. It's a gas, so it actually changes and becomes this stuff called aqueous carbonic acid. Now, the neat thing about it is we can use an indicator called Btb Bromothymol Blue, and bromothymol blue is blue until you mix it with an acid. If it, of course, turns greenish in color, that's a pretty strong acid, and a yellow is the weakest acid. If it goes back to blue, that means that it's fairly neutral in its overall concentration, right? Now, you're not going to get to do the lab, but this is the basic idea. You'd have 3 different beakers, one at room, one hot, and one cold with ice in it. You would throw the BTB and water in it, and then you'd do different things to the beakers. One of them, of course, you would heat up and throw the tablet in and see how the color changed. Then the other one, of course, would be nice and cold. You'd throw the tablet and see how the color changed. And then we'd add sodium hydroxide to cancel out the acid. The amount of sodium hydroxide we would use would help us to figure out, of course, how much acid was there to begin with. Our ultimate goal being to figure out how gases differ from solids in their solubility and how the solubility of a gas is different in water than those actual solids, right? Cool. Now, key things we can notice, of course, there's times when CO2 goes into those things, and one of the ways to look at that would be the results from this lab. In this lab, of course, we had 3 different tubes. This would be your room temperature one, this would be the cold temperature one, and this would be the hot. You would put a tablet of Alka-Seltzer in both of these. There'd be no Alka-Seltzer in this one. Instead, what you put in is the BTB. You put BTB in all of them, so it turns blue. Now, because there's no tablet, that means that there's no bubbles. There's no CO2. And the CO2 goes in and becomes carbonic acid. So if there's no CO2, there's no acid in the solution. That's why it stays blue. This is your control group. It, of course, is just there, and it's used for comparison so that when you go to neutralize them, they should turn back to that blue, telling they were at their starting spot, right? Then you got the hot solution. You throw a tablet in it, and, of course, it's hot, so it's increasing in temperature. When it does that, of course, it will change kind of a greenish color. It's very, very green, right? Now, key thing we should notice is then you have to neutralize the acid, and it takes less drops of the sodium hydroxide to neutralize the acid. Now, less base, sodium hydroxide, means that there was less acid. And if there was less acid, the acid was coming from the CO2. So that means that there was less CO2 that was in solution. That's carbonic acid. If I look at the other end, of course, I'd be decreasing the temperature with ice cubes. And when you do this, the weird thing is now you have to use more drops of sodium hydroxide to neutralize. Which means, of course, if you had to use more base, then that means the solution contained more acid. And more acid means that there was more CO2 in solution, which means a weird thing. That means for gases, if you increase temperature, because this one would be nice and yellow, very acidic, if you increase temperature, solubility of gases actually decreases. It's the exact opposite of these things called solids. And that all has to do with the fact that what gases are. Gases tend to be nonpolar substances. So when water is there with its charges, and I take those charges on water, it doesn't want the gas in the first place. So if I make it wiggle faster, and that's what I'm doing, I'm increasing temperature. Increasing temperature increases their speed. That's why we did gas laws first. Those waters are going to wiggle apart further, and then the gas can wiggle its way out. So as I increase temperature, gas solubility decreases. It's the exact opposite of solids. That's crucial to recognize, and it all comes down to charges, right? Always does. Now, an example of how this affects the Earth is the fact that, well, we don't throw Alka-Seltzer into the ocean, but we do burn a lot of stuff. And that means the air is full of CO2. That CO2 has to go somewhere, so it goes to the biggest thing on Earth, which, of course, on the surface is the ocean. As it goes into the ocean, it floods into there, and it runs into water, and it goes into solution. It makes carbonic acid. And then being an acid, it does what it does best. It dissociates and throws hydrogen ions, which burn all the coral and fish and destroy the ecosystem. Way to go, humans. This, of course, is called the process of ocean acidification. Now, one thing that we should notice, of course, this means that this acidification will be worse anywhere where the temperature was colder, like our seas in the Pacific Northwest, where most fish actually start their life in the most plentiful food-supplying oceans. The colder the water is, the more acid there will be from CO2 going into solution, because if you increase, of course, gas solubility requires you to decrease temperature, increase gas solubility. Now, the benefits of this is if we have a planet that's warming, which it is, that means that you will increase the temperature of the water like a soda sitting out. And as it gets warm, it decreases in solubility, which could help to, of course, bubble out a lot of that CO2. But the problem is it will have killed all the fish before then because we poured way too much Alka-Seltzer CO2 into the ocean. Not that this has anything to do with real life. It's just chemistry. So our targets today was to make sure that we could explain solubility curves. Hopefully you can look at this graph. I got this stuff called sodium chlorate, and I got this stuff called sodium chloride. Now looking at their lines, you hopefully notice that sodium chlorate has a much steeper slope, which means it, of course, is affected by temperature more than sodium chloride. Sodium chloride's fairly flat. It only goes up just a little bit. Now, both of them go up because as you increase temperature, you increase solids solubility, just like top ramen. But the sodium chlorate temperature has a bigger effect because, well, it's an RV. It's larger. So as I make the parking spots bigger, I can park more of it in. Whereas even in a cold ocean, you can fit a lot of salt in. Like our seas are still pretty cold so far. And, well, that's why lots of scooters can park in it. So it's always about size, shape, and charge, because all the things on this one have the same charge, right? So this is really about size. All right, thanks.